This video will focus on two learning targets. I know how to write equilibrium expressions, and I can predict if a reaction is product or reactant favored from graphical or numeric information. So in order to get into equilibrium expressions, let's just review what a reversible reaction is. A reversible reaction is a reaction where your reactants are making products, just like we normally think of as a reaction, but there's enough free energy available for products to go backwards and remake reactants. How that affects us, especially with the math we're going to look at, is that when the reaction stops, all of my reactant hasn't become product like it does when we do stoichiometric calculations. When the reaction stops changing, we have some reactants present and some products present, and that's what the equilibrium is. So equilibrium is a very dynamic process because even at equilibrium, where I don't see anything moving anymore, reactants are becoming products and products are becoming reactants. We just don't see a change anymore because the rates are equal. Again, mathematically, the problem is I can't stoichiometrically say if I have 10 grams of reactant and it all becomes product, the mole ratio will tell me what happens because all the reactant didn't become product. So essentially, we need new math to help us be able to calculate, once my reaction is not changing for a reversible reaction, how much of my stuff do I have? So this is the foundation of the new math. The law of chemical equilibrium is that if you take a ratio of the concentrations, so that bracket represents concentration, we'll be using molarity. So the concentrations of both products raised to powers of their coefficients divided by the concentrations of the reactants will be a constant. Okay, so K is just a constant. In this case, it's KEQ, which usually stands for K equilibrium. And that K is just a ratio relationship of product to reactant. Okay. K is temperature dependent, so if you change the temperature, you change the K. K is also process dependent. If I have a different equilibrium reaction, my K value changes. Okay, so it's really similar to some of the other constants we've been seeing recently in chemistry. So how this works with two examples, if I was to ask you to write a K expression or a KEQ expression, that would be a question of what does KEQ equal for this process? So you have to write your own equation for every single chemical process. It's always products over reactants. Okay, so it'll be HI over H2 and I2. And it's the concentration of the products raised to a power of its coefficient. So this would be the concentration of HI squared. And then we would divide that concentration by the concentration of H2 multiplied by, not added, so multiplied by the concentration of I2. Both coefficients are 1, so it's raised to a power of 1, which means I don't have to write it. If I were to do the K expression or the KEQ expression for this bottom one, same thing, products over reactants. So it's a concentration of PCl3 squared because of its coefficient. And then again, I'm multiplying, not adding, the concentration of O2. Then I'm going to divide that by the concentration of the reactants. And again, in this case, there's just one, and I'm going to square it because of its coefficient. The K value can also tell you whether the reaction is what we would call product favored or reactant favored, or forward reaction favored or reverse reaction favored. Okay, so the forward reaction would be product favored because I'm making more products going forward, and then the reverse reaction would be considered reactant favored because I'm going reverse to make that reactant instead. So based on the fact that K is products over reactants, if my K value is greater than 1, that means I have more products than I have reactants at equilibrium, which means that's a product favored or forward favored process because that's how I get a K value that's greater than 1. If my K value is less than 1 at equilibrium, that means I have more reactants than products, because the only way to get a number less than 1 would be to have my denominator bigger than my numerator, and therefore that would be a reactant favored process or a reverse reaction favored process. So K greater than 1, products favored, K less than 1, reactant favored. The only other weird thing to know about writing K expressions then is that K is actually dependent only on gases and aqueous things. So it turns out if the reaction is reversible, and in that reaction you have any solids or liquids either as reactants or products, their concentration values are not reversible. Okay, so they kind of go through normal stoichiometric reactions as they proceed. So for this particular reaction where we look at like the decomposition of calcium carbonate's a solid, it makes another solid and a gas. If we were to write a K expression just like I instructed with products over reactants raised to a power of a coefficient, we would have that middle reaction there. But it turns out that the equilibrium expression is solely determined by things that are in the gaseous phase or things that are aqueous. So the actual K expression for that reaction is just K equals the concentration of carbon dioxide. It's a little weird, and you're not going to see a lot of solids and liquids, but you do need to be aware of it because it does change the math. So K expressions are always products over reactants raised to a power of their coefficients, but only for those substances that are either gases or aqueous things. That's it for this video. Go ahead and do the quiz and have a nice night.